We decided to record this so that you could have the benefit of hearing class. So hope wherever you are, you're doing well. And here we go. So we're looking at number 22 on page 40, and we've gotten as far as identifying the information that's given to us. The 23 meters per second here is the initial velocity, and rest is code word for a velocity of 0. That's our final velocity. And the delta x is the distance of 85 meters. And now the question is, what is the car's acceleration, which is assumed constant? So I bust out my two equations of motion, looking for something that I can plug into. And I get v equals v0 plus at. And when I plug into this equation, I have v, which is 0, and I have v0, which is 23, but I do not have a. In fact, I'm looking for a. And I also don't have t. I don't have the amount of time. I don't know the amount of time that it takes for this thing to slow down. At first you think, yes you do. No, wait, that's a distance. I've got a distance, but I don't have a time. So since I have a distance or a displacement, I say, okay, let me try delta x equals v0t plus 1/2 at squared. Let's do that in a different color so it's clear that that's a different equation. Blue. And I go plugging into that equation, and I get 23t plus 1/2 at squared is equal to 85 meters. So again, I have the same two variables that are unknown to me.
T's
What's that?
time takes 7.4 seconds.
Very possibly. How'd you get it?
What I did was, as I did on the first year's screen.
But we don't have that equation yet. That's a shortcut that you'll learn on the video. He knows this because he gave us reading ahead.
So, you can't use the formula in the book because we said that t equal to negative 23 plus a, and then do something for the bottom equation, and then everything equal and solve for a.
That's exactly the right idea. There was something about your algebra that was a little off. It's not plus. Yeah. Okay. So, here's what I want us to observe. Now that we have set up our two equations of motion, we observe that we have two variables. And we're going to do a variable and equation count. How many variables do I have? 2. How many equations do I have? Also 2. If the number of variables and the number of equations are the same, we are good to go. We can solve. The fact that I have two equations and two variables is a green light for me to now go solving with the two techniques that you learned in Algebra 2. And what were those two techniques for solving systems? And combination or elimination, that's right. So our two techniques are going to be substitution and elimination. Now, I think in Algebra 1, you had a very limited idea of substitution, which is that you always solve for one variable and then you plug into the other one. We're going to take a broader view, and here it is. If you see an equal sign, that equal sign is your license to substitute. So, for example, I see here that this expression 0 equals 23 plus AT. If I find anything that is exactly 23 plus AT, I can substitute 0 for it. Or, if I find anything that is exactly equal to AT, then I can replace that with negative 23. And in fact, I do have something that's just about AT. It's not quite AT. It's 1/2 AT squared. So I'm going to be a little bit clever, and I'm going to write the 1/2 AT squared as 1/2 of AT times T. Does everybody see why I might want to do that? Because I know what AT is. And so now I can substitute in here, and lo and behold, one of my variables has now dropped out of my equation. And I get a nice simple equation. 85 is equal to 23t minus, well, 1/2 of 23 is negative 11.5. So that when you simplify this, you get 11.5t. And then t is equal to 85 over 11.5, which according to the magical plastic brain is 7.4, which is what Jesse had told us using super duper magical shortcuts that we learned by reading.
Wouldn't we, I mean, it's the same sort ways of solving.
They ultimately end up being the same, that's right.
I
Which
mean, like
will
the
come out on
process
the-
23t plus 1/2 times negative 23 times t. That should be the same.
Yeah, yep. Yeah, they're all interconnected. There it is. Yes, sir.
When we do this, do you want us to put in our units?
That's a great question. When you're dealing with the equations right here, I want units to show up in the initial plugin. I don't have it here because I was being silly, only to make sure they're consistent. The students will sometimes get dorked up when the displacement is given in furlongs and the speed is given in meters per second, and you forget to convert. That's a real common student thing. So if you do the plug-in with the units here, then you can sort of drop the units and let it come back. I'm cool with that. Okay. Now this is not the only way I can substitute. So for example, if I didn't see to do this, which was a little bit clever, wasn't it? Then I could also have done t equals negative 23 over a. Josh, that's what we were really looking for, was the divided by a. And now I can substitute my t equals negative 23 over a into here. And the advantage of that is that I get an equation that involves a, which is what I was looking for. Just like that. And this gets me that 23 times negative 23, which is slightly intimidating, but it's not too bad, which is negative 5.9 over a plus, let's see here, we have 1/2 of negative 23 squared, which is 265. And we also have a divided by a squared, like that. And now I observe that I have a variable in the bottom, which I can handle by, you know, the strategy of clearing the fractions for equations, multiplying both sides by the common denominator so that we get rid of fractions. So if I multiply both sides by a, then lo and behold, my factors of a cancel out, and I get negative 529 plus 265, which is negative 265. And a is therefore equal to negative 3.1 meters per second squared. So this would be a second way to solve by substituting. Yes, ma'am?
Why is a divided by a squared equal to a?
It's equal to actually 1 over a. Yes, as we have here. So we have one factor of a in the top and two factors of a in the bottom, leaving us with one factor of a in the bottom. Yes, no? Okay. Good. I saw the eyebrow. Okay, so this is how substitution would go. The elimination turns out not to be very profitable for this particular case, so we won't bother to do it. But we see that there are a couple of ways to substitute. Questions? Great. Let's take a look now at number 20. think it's 23. Yes. I think number 23. And in this problem, a light plane must reach a speed of 33 meters per second for takeoff. Yes, it was. How long a runway is needed if the constant acceleration is 3.0 meters per second squared. Acceleration. No. Acceleration. That is spelled correctly.
Wait, what does it give you when you check?
Oh, it gives me, oh yes, you spelled it correctly, I just didn't bother to tell you. Okay, so since you guys did this for the homework, let's talk it through. Grant, what do you get from the two equations of motion? First, I'm sorry, what do you get in terms of identifying our quantities?
Velocity.
Great question. Is this an initial or a final velocity? And how can you tell? How do you know? Yes, that's right. So we actually have to visualize the motion happening. We picture that plane. It's going to be starting. What is it? How is it going to be starting? At 0. Actually, it's probably going to be starting at like, a half a mile an hour as it taxis down the runway and the captain tells that jokes. But there it is. So we have a final velocity that is at the end of that acceleration process. So visualization of what's going on is definitely a necessity for these problems. You can't just go on autopilot and just start hoping that the numbers mean something. You have to picture what's happening. Okay, keep going.
The constant acceleration.
This is my K, and we said something in passing. We said that the initial velocity was 0. Okay, good. What can we figure out from this?
Equal to VO plus equal.
And you may or may not know if this is the right equation ahead of time. Sometimes you just have to try one and see how far you get. So do not feel as if you have to know necessarily which equation you are definitely going to use for this. Just try it. See what happens. And when we try this one, what we see is that we have v is equal to 33 meters per second. Initial velocity is 0. Acceleration is that going to be a plus 3 meters per second squared or a minus? Like the plane is being pushed forwards. It's really pulled forwards by the propellers, right? Okay. What can you find out from this equation? And what is t? Do it in your head. T is 11 seconds. Mentally check that, plug back in. Yeah. When you solve these equations, take 10 seconds to check your answer. You get a number, plug it back in and make sure that it's right. You'll be happier with yourself when you do, because that'll help identify if there are any mistakes, which means that you'll get a greater percentage right, which means that you'll get a greater percentage in the class. Okay, so we got t equals 11 seconds, and I put a box around it and smile and move on to the next problem, right? No, why not? Bingo, I haven't answered the question yet. So how do I answer the question? Keep going, Olu. Uh-huh. Great. Good. Now, what are all the values that I know? Mhm. What is it? What's the value? 0. Mhm. Yes, exactly. Notice that anything that we have been previously given or that we have previously found is still true. And so my t is still 11 seconds right here. And so I have a half of, excuse me, 1/2 of 3 times 11 squared. Now, if we're clever, we can do this in our heads just by remembering that multiplication can happen in any order. What's 11 squared? And what is a half of 121? 16.5. What's 16.5 times 3? 125. It's 182 meters. Look at that. We did it in our heads. Just by reordering the multiplication.
Where do you get your safe bait from this equation?
That's a great question. I would actually...
I rounded down to 180.
Yes, that's actually correct. I was so happy that we had gotten our answer without needing to resort to the plastic brain that I just didn't clean up. So you'll catch me not cleaning up too. Good. Now, how does this fit into our new problem-solving technique? Well, actually, it fit very nicely. We ended up with 2 equations and 2 variables, but in this particular case, one of those equations had only one variable represented, which made for an easy solve and then an easy substitution. So we like that if we can find a situation where that happens. But this still ended up being 2 equations that we needed in order to solve the problem. Does that make sense? Okay. 3s. Group of 3, U3, U3, and U4. Let's do number 24 together. Getting groups?
Question.
3 and
22 and 24 part tonight's homework.
Yes.
So, is that, do this,
No.
you still want us to do them?
Yes, do them clean. Doing them a second time makes them stronger, better, faster type of problems. Okay.
Okay.
Yes. Really not listening to me.
blocks. I was like, why are we bursting through blocks?
Yeah. Catherine, you over there? Who's the really good sprinter? What country that took Olympics, I guess?
That bold guy?
No, girl. What country? U.S. No, not that one.
Wait, who got a medal?
Marion Jones, yeah. There's been a lot of that. One of mine, Carl, shoot, what was his name? He was a big Olympian in the 80s, sort of inspirational to me. He got his medal stick.
Michael Phelps is really sweet.
Wait, so,
At this point, if you're watching at home, I'm actually going to pause the video, or actually stop it, so that you can do this on your own, and we will see you tomorrow.